Okay, so welcome back to our third week of this advanced machine learning course. And last week we started with a review of neural networks, because this is going to be a stepping stone towards the final parts of project number one. And we are going today to present also the data sets, which I'm going to propose, which people can work on. And I will also outline the three different paths which we can take in the beginning, so that you have the possibility to tailor the project to your own interests. Now, this is the official GitHub address of the course, but the official University of Oslo page is the one which you probably have looked into already. And this is given by the Physics 5429. And there you will find the weekly schedule. Now, the weekly schedule today is a little bit changed, as you can see from the GitHub address. So if you scroll down here, you will see now that what we're going to spend a little bit time on today is actually to discuss the codes for feed-forward neural networks. And many of you have written such a code already. And today I also wanted to remind you of some of the basic ingredients of neural networks. And then we are going to look at the data sets which we can study in order to get started. So I'm going to propose three different paths. And for those of you who are more interested in physics simulations, this is going to include the generation of data for solving differential equations and how we can train a neural network to simulate the next time steps in the solution of coupled ordinary differential equations. And then we can use this later on as we move on to more complicated differential equations. So there will be a physics axis. There's going to be a more computational science physics axis where you develop a code yourself, or let's say convolutional neural networks. And then there will be another axis where some of you are more interested in applying convolutional neural networks to specific problems like image recognition. So that will be a third variant of the first project here. And then we'll see how things develop. Okay, so today, this is basically the plan. And I'm going to show you how you can use either your code or codes which we have placed in the lecture notes. So if you look at the lecture notes for this week, the slides which are there deal with how to construct a feed-forward neural network. And for those of you who have taken physics, Phys STK 4155, you have already seen this before. Video and lecture notes will be available afterwards. The video from the last lecture is up here, as you can see. This is from last week. So you will find this material being uploaded right after the lectures. That means the video and the links to the handwritten notes. The other thing which I wanted to say is that if you go into the doc folder and you click on programs here, you will find a code for neural networks, which has actually been developed by Greg, who is attending this course, and Eric Reber. And this is a code which we will discuss briefly today. And it contains a more systematic way of setting up your own code for a neural network. There's also the possibility, if you don't want to use your own code, to use, let's say, TensorFlow or PyTorch in order to set up a neural network. So you can, in a way, choose the path you want to explore. If you want to more get straight into the data, you can just use TensorFlow or PyTorch in order to set up a neural network. If you want to write your own code, this is also an equally viable approach to project number one. So we want to give you as much flexibility as possible when you are working with the projects. There's also an example code for solving differential equations, which you will find useful in generating your own data. And I'm coming back to the kind of differential equations which we are going to look at. So this code ODE example is more tailored to the solution of a Newtonian-like problem, but you can use that one if you want to, instead of setting up a ordinary differential equation solver for the Lorentz system, which we're going to look at. So this Lorentz attractor system is a famous set of coupled differential equations, which has been used in studies of chaos. And there, what we are going to do is actually to set up an input matrix for a neural network, which will contain the previous time step. And then we do an output, which contains the next time step. And we will use the differential equation solver with various initial conditions to generate new data. And we are going to let the neural network make the predictions with you given the previous position at a given time step, and use that one to predict the next one. So this is the basic physics or ordinary differential equation problem, which we are going to look at as our first data set. But as I said, if you wish to study more convolutional neural networks and neural networks for imaging, this is a alternative to what we are proposing today. Feel free to break in, unmute yourself, or just put questions in the chat. I will try to make this more visible throughout the lecture today. The other thing which I wanted to do before we begin now is to remind you quickly of what we did last week. So let me just bring this up, and a quick reminder of what we did. So this is from the handwritten notes from last week, and I'm just going to bring up the topic which we discussed, and we put an emphasis on automatic differentiation. So last week we started with a basic review of how to set up a neural network, and many of you do have such codes. Now, in the material which you find online, you will find an alternative to the lecture notes we discussed in Physics SDK 4155. And you can use that code, or simply just use your own code from Phys SDK 4155. So the thing we did was to look at the architecture or the model, and then we looked at the next item, which is the cost function and optimization and regularization. So the architecture is defined by the hidden layers, and the architecture is synonymous with a model. And in this case, we have hidden layers, given number of nodes or neurons or units, as we normally call them, and then the type of activation functions. The next thing is the optimization part, and the typical problem which you encounter when you do a regression. You're trying to fit some data points to a specific function. Then you would typically use the mean squared error as the function you want to optimize, which is the cost or / loss function. And what we did then was to look at the optimization parts, and there are several ingredients here. And that code which I mentioned, which Greg and Eric have developed, which is essentially an extension of their project 2 for Phys SDK 4155, contains all these elements which you see here, in addition to having the different types of activation functions. So the optimization part is something which we need. If you prefer to use TensorFlow or PyTorch, all these options are baked in. So in the beginning, I was thinking that we should use our own code, but you should feel free to actually use these ready-made programs. In particular, when it comes to convolutional neural networks, and adversarial networks, and also autoencoders, it's much more convenient to actually use one of these libraries. And then there was a list of activation functions, which we discussed. We discussed the universal approximation theorem and the structure of a neural network. And the important algorithm is an algorithm which is called the backpropagation algorithm, which is the same as reverse mode in automatic differentiation. And we gave you a simple example of a problem which had only scalars. There were no weight matrices, no bias vectors. There was just one weight parameter. And then with that simple example, we could then compute the gradients of the cost function with respect to the two unknown parameters. And when we had the gradients, when we did the algebra here, with the gradients, which were given by these analytical equations, then we could then set up an algorithm for updating the two parameters, W1 and W2 here. And these are typically iterated back and forth with a forward step and a backward step till our cost function doesn't change or stabilizes after a given number of iterations. And the essential part now is actually we have these unknown parameters, theta L, which is now a kind of container for all the unknown parameters. And then we would simply use the chain rule to propagate backwards to the first hidden layer, as you can see here. And this application of the chain rule is what gave us the standard backpropagation algorithm. So I'm going now to just remind you quickly of the automatic differentiation and what that is doing. And then you will immediately see that this is the same as the standard backpropagation algorithm. And the example which we looked at was a simple example of a function in order to illustrate the way automatic differentiation functions. So if you were to encode this function, or if you were to use some symbolic packages like Mathematica or SymPy, they have the functionality where you can translate, let's say, the derivative into, let's say, a C++ code, or a Fortran code, or Python code, or I even think you can translate into Julia. And with that, what often happens is that the code which you end up with is written in a not very efficient way from a computational point of view. So the derivative which you see here is typically the way Mathematica would produce a derivative of this function, and then it would translate this into code as it stands. And then you would have to speed it up. And if you were to do this in a very, how to say, brute force way, you see now that the function itself, which you have, and the derivative is a more complex function. So one of the advantages of using automatic differentiation is that the number of floating points or floating point operations needed to calculate the derivative is going to be at the same level as calculating the function itself. And that's a big advantage of using automatic differentiation. So in this specific case, we did a very, very brute force approach to the derivatives. And we simply calculated everything step by step. And this is obviously a very inefficient way of doing that. So you would typically rewrite the function itself in terms of an intermediate a, and then you would calculate the exponential of a. And that would reduce, if you now assume that the number of floating point operations take the same time, then that would reduce the number of operations from 5 flops to 4 flops. Then the derivative, if you don't do any kind of smart thinking, contains now in the numerator 4 floating point operations, in the denominator 5, and then there's a division. So that gives you 10 floating point operations. And what you see here is that the derivative itself, with no thinking, actually gives you twice as many floating point operations. So this is one reason to avoid using automatic translations with symbolic packages like Mathematica or symbolic Python. The other method which is widely used is actually the one of finite differences. And we discourage you using finite differences because it will depend on a delta x here. And it will also, if you make delta x smaller and smaller, you can enter the area of round-off errors, because you cannot represent all numbers, floating numbers, precisely in a computer. And that means if you have round-off errors, you can easily obtain loss of numerical precision. And then your derivatives live their own lives. And you are basically on your own. So automatic differentiation is a fantastic algorithm, which if you write your own code, this is something you have to implement. Now, the automatic differentiation, which we looked at then, so let's quickly repeat it, and then we jump into the whiteboard. is simply to set up this function. And what we looked at last week was the forward mode. And I'm going to go through the different details here. So I'm going to set this case up again so that you can see how automatic differentiation actually works. And then we're going to look at the more general setup for automatic differentiation. So I'm going to repeat a little bit this case, which you see here. And then we are going to perform these different operations, which we didn't have the time to do last time. When we are done with this, I'm going to switch over to the general structure of a neural network and how the code could look like. And after that, we are going to look at the data we can generate. And you have functions in the lecture notes and the material online, which you can use. Or alternatively, as we said, you can use your own code from FIS SDK if you're happy with that one. Okay, so let's now switch to the whiteboard. So this was just a quick reminder of what we did last week, just to bring up some of the basic elements of what we have for neural networks. Okay, any questions so far, guys? Is everything crystal clear? Okay. Excellent. So let me bring up the whiteboard. And let's now finalize this discussion of backpropagation and automatic differentiation. So what we have is this simple function, f of x, and it's simple enough so that we can actually run through it in a lecture, and at the same time illustrate the basic elements of automatic differentiation. As we said last week, and also in this quick review, if we don't think, this function here requires 5 floating point operations. Now, the derivative contains then, if we also don't think, 10 floating point operations. So what we're going to do now is actually show that we can have a number of floating point operations, which is comparable to the calculation of the function itself when we evaluate the derivative with automatic differentiation. So we defined intermediates, a function a, which is x squared, and then a function b, which is the same as the exponential of a. And we defined a new function, which is c, which is a plus b. And then we had a final function d, which is the same as the square root of c. And now you see we are back to the function. That is the same as our function f of x. Now, when we draw this automatic differentiation chain of operations, what we would typically do then is to use a graph. And this graph is pretty close to the way we think of a neural network. So x feeds into a. And in a, we are doing a squaring of the argument x. Now, a is then sent into this function c, where we have a plus here. So that leads to c. But there is also a branch here where we now compute b by an exponentiation here. So that takes a as argument. And then c is now brought over to d. And then we have a new operation here where we take the square root of c. And finally, this d is the same as our function f. So this leads to f, then the final one. So this is a typical graph which we would set up. And if you think back of a neural network, you could now think of x as your input to the neural network and f as your output. And that feeds into the cost function. So if you now look at the so-called forward mode, this is a mode where we would start with x. And in this case, there's just one argument. So one of the reasons why we normally use the reverse mode is that in the reverse mode, we typically have very few arguments or very few function values. Whereas if you think of a neural network, the input layer can contain thousands and thousands of inputs. Now, if you now look at the forward mode for autodiff, what we would have then is something like a d of a of dx, which obviously is equal to 2x here. And we would set up dB of d of x, which is, if we use the chain rule, and I hope you guys don't get offended if I go through these basic steps here. And then finally, we have dc of dx, which is going to be given by dc times dA. So we have a dependence on both a and b, so we need to include both. So we would have a dc dB of d of x. So that would be the derivative of c with respect to x, because we need to take the derivative of both b and x, or b and a. And this is something which we can then rewrite, and you will see that this is pretty obvious. D of a dx plus dc dB, and then we have dB, and then we use the result which we have from here and plug that one in. So we would simply have a dA of d of x here. And this is actually pretty straightforward to set up. And the next thing which we need then is to look at the d, and this is going to be a function of x as well. So that is the same as d of dc of d of x. And we have dc dx from the previous step here. And the final thing which we need to note now is that this function d is just our f. So this is now the same as d of f of d of x. Now, if we look at the function d of dc, that is nothing but 1 over 2 times the square root of c. So that means that what we need to plug in now is simply the expression for 1, so df, d of x now, is given now by 1 over 2 square root of c, and then we have a dc of d of x, which is the equation which we need from here, and where we have this one defined here. Now, if we now look at the expressions which we have, we know that the way we have defined this function a, this is given by a and b. So that means that this quantity here is simply equal to 1. And this quantity here is also equal to 1. So we have a pretty easy thing to do now, because what we need is simply dB dx, and then we need to have dA dx here. So, and dB with respect to x, the derivative of that one, is something which we have here. So if we then collect everything and plug in this expression which we have, then what we get is the following. So if we put everything together, what we get then is x times 1 plus b divided by square root of c, when we plug in everything here. So what you see now is the following. If we now think a little bit, we know that c is the, when we use that one, c appears in f of x equal to actually the square root of c. So that means that we can pre-calculate, because often if you now think of the back propagation and you have an activation function like the sigmoid, the derivative of the sigmoid function contains the sigmoid function itself times another function which contains the sigmoid, which means that we need to calculate the function itself. So we could now pre-calculate this square root of c. So that's already done. And then we would also pre-calculate b. So if these quantities are now pre-calculated, that means that df dx, the number of floating point operations, if we do the count then, So we have already calculated c and the square root of c in the calculation of f of x. We have pre-calculated b when we calculated the f. So that means that the 4 floating point operations in the evaluation of f, they have already been done. So we don't need to calculate b. We don't need to calculate the square root of c. The only thing we need to do now, if we do the floating point operations, is that we have x, which we need to multiply with 1 plus b. So b is pre-calculated. We have an addition here, and then we have a multiplication. So that's 2 floating point operations. And then we have a division. And if we do the same thing as we said last time, we assume that all operations take the same amount of time, which is actually not true. Then you see now that the number of floating point operations here is equal to 3. So this is down from 10 if we didn't do any thinking. So we can actually save a lot of floating point operations when we now use automatic differentiation. Now, this was the forward mode, which you saw here, because we started with dA dx, and then we moved on forward. But we could actually start with the df dx and work backward. So we should obviously get the same expression. For this specific case, we are not going to get any improvement in number of floating point operations. But when you start with a neural network where you have very few outputs, which is a typical case, could be just one output if you have a function value, or if you have, let's say, some images you want to reproduce, like the handwritten numbers, you would have 10 handwritten numbers from 0 to 9. And then you could feed in your input layer, you would have something like perhaps 100,000 images, and each of them have, let's say, 20 times 20 pixels, just to give you a number. So that means you have 100,000 times 20 times 20. So that would be the number of input parameters of which you would calculate this df dx. This is not entirely true for a neural network, because for a neural network, we are not using the derivatives with respect to the input layer, but we are calculating the derivatives of the hidden layer with respect to the weights and the biases for the hidden layers and the final output layer. And still, these can be pretty many parameters. Okay, so if we now look at the reverse mode, this often can involve less operations. So if we now look at that one, we have a df dx. And actually what we would do if we take the reverse mode is that we need to calculate df dc. So if you go back to the graph, because we know that d is the same as f in this specific example. So d here is the same as f. So that means that the next derivative is actually c. So we have now a df dc. And if we now just use the chain rule here, we start with d. So we would have d, dod, and dc. And we know that this one is just equal to 1. So this is the same as d of d with respect to c, which we have seen before, which is 1 over square root of 2 times the square root of c. Now, the next thing which we need is to find the derivatives with respect to the inputs to c. So we would need df db, which would then be simply df dc, and this is the same as dc db. I should actually decide whether I use partial signs or not. So this is df dc. And if I do that, you see now that the dc with respect to b, this quantity here, we know that that one is just equal to 1, because c is equal to a plus b. And then I'm left with df dc, which is now simply 1 over 2 over square root of c. And then I need the same quantity when I take a. So I have a df d of a, and that's going to be given by df because A enters B, so I need dB of D of A plus dF, dC, and then dC D of A here. And you can see that immediately from the graph, because A, if we go back to the graph here, you can easily see that because A enters B, but it also enters the definition of C. So that means that when we take the derivative, we are now going in here, but we're also going in here in order to come to the final point here. So this means that when we now put this up, what we end up with is simply 1 over 2 over square root of C multiplied with 1 plus the exponential of A, which is the same as B. So this is nothing but 1 over 2 square root of C, and then we have 1 plus this parameter B here. And then the final step, which we need now, is simply to do dF of D of X. And dF D of X, the only place where X appears now explicitly is actually in B. And if we take that derivative, so this is going to be dF dA of dA of dx. And that's the final stage which we need to think of now. And when we have done that, we get back the same expression which we had before, 1 plus b divided by 2 over square root of c. So if we now, as I said, have pre-calculated things, this is actually much easier to evaluate than a standard symbolic manipulation. So if you also look at the number of operations we do in the back propagation, the number of derivatives which we have is actually less than the number of derivatives operations we have to do in a forward stage. So the backward stage is often preferred when we perform automatic differentiation. So automatic differentiation is actually a formalization of this example. And let me just write down the basic algorithm here. So autodiff is a formalization of this example. And assume now that we have, and I'm going to write down the basic algorithm. Assume we have x1 up to some xd input variables. And I'm going to link this to the example which we saw here. So let's say we have these input variables. And from input variables to what we are going to call xd plus 1 to an xd minus 1, which are the intermediate variables, as intermediate variables. So you could think of x1 to xd, lowercase d, as the weights which you have in a hidden layer. And then the other quantities would then be the parameters, which are variables, which you have for every given hidden layer as intermediate variables. And then we have an xd, x uppercase d, is the final output variable. So that would be the output from a neural network, which then is fed into the calculation of the cost function. So if you look at the specific example which we have only one, x1, which is equal to x. And in our case, for that specific example, d is equal to 1 in our example. And then the intermediate variables, x2 would be equal a, x3 would equal b, and x4 would equal c. And the final variable, xd, the output, is then given by d, which is equal to the function itself. So what you would need then is the following. So the following way is the way the feed-forward mode actually operates. So for I equal d plus 1 to the final value d, then we will simply calculate these intermediate variables, xi, which are given by specific mathematical operations, which now contain as input to this the previous variable, x of I here. So this g of i's, they are what we normally call elementary functions. And this x of PA of x of I, they are the parent nodes of the variable xi in the graph. Are the parent nodes of the variables of the variable x of I in the graph, which illustrates how this function is calculated in terms of intermediate steps. So what you could say now is that this function g2 is actually given by the squaring of x, and that is given by this variable a. And then we have g3 here, which is now simply the exponential, and I'm just putting in the argument. So this actually receives a. So that's the result from the parent node. And g4, if we link it to this example, is nothing but this variable c, which is simply a plus b, which in our case is g2 plus g3. And then I would have my final g5, which is simply the square root of c. So that means that the parent is now given by the square root of c, and that gives us the final variable d here. And by definition, what we have is that df dxd, when we now set up in terms of partial derivatives, this is equal to 1, because xd is equal to f. So that's the output. And the reverse mode, or back propagation, so the reverse mode, when we set it up then, or back prop, and if you go back to the slides, the handwritten notes from last week, you will see that this actually is the same as what we did now. So df dx of I, one of these xi's, is now simply given by the sum over these xj's which we had, and where the xj's, or the x of i's, actually given by the variables xj, and you can quickly see that when you write it out in terms of this simple example. So you would have an xj of d of xj and d of x of I here. And if you go back to automatic differentiation, this is, the back propagation algorithm which we had, this is nothing but the way we implement the back propagation algorithm. So the link between automatic differentiation with reverse mode and back propagation is something which is actually not that well known in the machine learning literature. So automatic differentiation works whenever we have a function that can be expressed as a computational graph, where you have elementary functions which are differentiable. And the functions may not even be a mathematical function. It could actually be a computer program. So automatic differentiation is an extremely powerful algorithm. And normally what I recommend when you are setting up your code is to try to use automatic differentiation with AutoGrad, or alternatively to use the JAX, because that gives you also much more flexibility in calculating derivatives of cost functions, because then you can play around with different types of cost functions. And with having that flexibility means that you can simply, with AutoGrad, you can play around with different cost functions without the hassle of one, calculating the analytical derivatives, and two, which is a very, very error-prone process, to translate your analytical derivatives into a program or a function. And if you ask me, this is often the stage where I make stupid errors. I may have a lengthy expression for the derivative, and it's so easy to interchange subscripts or indices, or just ignore some specific quantity. So, and that can lead to hours, or in the worst case, weeks of debugging and finding stupid errors, which you made simply because you rewrote the function in an erroneous way. You had a small stupid error. I once, when we meet in person, I can list all the kind of stupid errors I've made. So I see there's a question in the chat here. Actually, there's an important thing in the chat here. So when we are going to look at the code, you should keep in mind that if you're writing programs in Python, Autograd is no longer maintained, as Greg says in the chat here. And JAX is actually a smarter choice because it also contains efficient ways to parallelize your codes and optimize your code. So JAX has replaced, to a very large extent, Autograd. So, and this is one of the things which can be useful to explore when you now are writing your own code. So the other thing which we touched upon loosely last time is actually the different ways of optimizing the gradients. So in a typical neural network, we are ending up with something which is called the backpropagation algorithm to calculate the weights and biases and have an update for them. So let me just quickly remind you of the kind of equations you would plug in when you now are setting up your neural network. And these are all listed in these lecture note links from Phys SDK, which I gave you. So if you have a neural network, what we are going to have is a set of parameter theta, which are going to contain the weights for the different layers, weights and biases. So these are matrices and vectors. And this continues depending on how many layers we have, till we reach the final output layer, which we normally label with an uppercase L. So these will be the parameters which we need. And then we have a cost function. So we will define a cost function, which depends on the output and obviously this collective set of parameters. And then we use backpropagation, or this reverse mode, to calculate the different derivatives of the parameters W1, B1, etc., etc. So if you go back to that simple case, which I put up in the previous lecture, that is an example on the type of equations which you end up having to code. So the basic equations which you would need would then be to calculate this cost function at the final output layer. So this is going to give you an equation for the cost function, the derivative with respect to the weights. And we can define that in terms of a parameter. So this becomes now a vector. And these parameters are given by the Hadamard product, so which means that if you have two vectors, and these vectors have elements A1, B1, no, A1, A2, and then there's another vector which has B1, B2, and so on. So the Hadamard product is actually the component-wise multiplication. So A1, B1, A2, B2, A3, B3, etc. So I just rewrite this in terms of the output. So this is the output from the hidden layer. So this is an L-1. So this is an output from previous layer. These are the explicit expressions. And you would normally then also define this parameter delta, which you have here. So this would be delta for the output layer. And then you would calculate these quantities for the various other layers. So this delta of L here is actually given by the derivative of the activation function with an argument to the last layer, which then also contains the derivative with respect to the output from the last layer. So this is the input to the last layer, C of L, and then we have an output A of L. And then we can calculate also this parameter. You can show that this parameter is given by dC of dB of L. And finally, we need this one for the final output layer. So I'm just going to put in a specific coefficient here. So not for the final output layer, but for an intermediate layer till the first layer. And we can actually show that this quantity here is given by a sum over K. And this is where we've just used back propagation or reverse mode. So we have a layer L plus 1. We have the weights of K of L plus 1. And this is then multiplied with the derivative of the activation function with the input C of L. So all these quantities are defined in the lecture notes. So that gives us then an algorithm for setting up the weights. So we would have now the weights in a specific layer. So this is a training, and this is solved iteratively by some gradient method minus a parameter eta, and then you have a delta J of L, and then you have the parameter AK L minus 1. So I'm writing this out in terms of the specific indices. And then we would have the unknown parameters, the so-called biases, which are given by the previous value, minus this eta, which is the learning rate, and then the gradients of dC of dBJL. And this is nothing but the previous value minus eta times this delta J of L here. Now, this procedure with the back forward and the forward stage is continued till this cost function does or stabilizes. These are the explicit expression, and these are the expressions you will see in the calculations here. So eta is a parameter, which is the learning rate. And this learning rate is now something you can fix, or you can have an iterative update of it. So we could actually put this one as a function of a specific iteration. And we would then use something like ADAGRAD. So that's one type of scheduler, which is very much used. We have the root mean square propagation. And then we have another method, which is highly popular in the literature, and that is ADA. So these are methods which are then used to update the learning rate, and we need the gradients. So back propagation or reverse mode in automatic differentiation is nothing but an algorithm which gives us the derivatives or the gradients which we need. And then we have a standard gradient descent or stochastic gradient descent in order to find the optimal values. And that's the basics of a neural network. So after the break, we are going to look at 3 specific paths for project number 1, or the first part of project number 1, whatever we might end up calling it. And we are then going to look at a specific set of coupled differential equations. And then we go back and we look at the codes or how we could structure a code for a neural network. I'm stopping the recording now. So before we dive into the specific writing of a neural network code, what I wanted to sketch now are the possible paths in order to get started. So one thing which I'm still waiting for is a complete answer for the questionnaires. But what I would like to suggest is that we have either one large project, or that we can break it into 2 different projects. And these will form something like 70 to 80% of the final grade. And then we could have a final oral examination, which the study administration wants us to have. And that could count something like 30% of the final grade. You should feel free to obviously collaborate. And I'm still waiting for some input to the questionnaires. And as soon as I have that, I'm also going to suggest the working groups, depending on the inputs which you've given. But what I wanted to present to you now are the following paths for the first part of the project. So we can think of this as project 1 and project 2. You should also keep in mind that this course is more a kind of self-study course, which also means that besides the lectures here, you should feel free to rewrite or redefine the projects according to your scientific interests. So what I'm proposing here is something which will link up with the lectures which I'm presenting, but that does not mean that you should feel constrained by my suggested boundary conditions. So let me just list the paths for the project here. Project 1, or we just could call this part 1, project 1, or the first part. So we are going to have as a main topic, this is deep learning. And the methods which we are going to present are 1, a standard feed-forward neural network, which we have revisited now. We are going to look at convolutional neural networks. We are going to look at recurrent neural networks. So these are some of the more popular methods. And then we are going to have autoencoders, variational and normal autoencoders. And then we are going to have general adversarial networks. So these are the 5 topics which I will cover in lectures. Now, based on that, as a kind of common overarching denominator, what we're going to have then is the following. So there's a path 1. And to get started, we are going to solve ordinary differential equations. And here I'm going to explain to you what kind of data we will generate, what they're going to look like. And I'm going to propose 2 types of differential equations, one simpler, and then we have this Lorentz attractor, which has been very popular in studies of chaos. So solve ordinary differential equations. What that means is that we are going to have, and now x can be a vector, at the time step t plus 1. So this is a time dependent, so this is a dynamical problem. You could think of Newton's equations, for instance. So this is a dynamical problem. And this is now given in terms of xt, the previous value, plus your ordinary differential equation solver. So I'm going to write this in a generic term as an ODE solver. Now, in the codes which you will find online, this is essentially a Runge-Kutta to 4th order, an RK4. And some of you may have met this method when you took computational physics. So that's the code I'm going to give you. But you can look at other methods like a velocity-Valère method, which is very useful if you have energy conserving systems. So the type of equations which I'm suggesting you are dynamical ones, and they may not conserve energy. Like one of the examples is actually with a applied external force on a harmonic oscillator plus a friction term, so it dissipates energy. So it's not an energy conserving system, and then typically people use a Runge-Kutta solver. So this is the first path. And now, if you think of what you're going to do now, you're going to generate many solutions with different initial conditions. So we're going to set up a series of initial conditions. So every set of initial conditions is going to give us a path. That means the value of x here. Then the input to the deep learning method, input is, depending on all these initial conditions, is x of t. So you can start with initial values, and then you make a prediction based on your ordinary differential equation solver for xt plus 1, which would be x1 in that case. So that means that the output, which is going to be the target in the neural network, is going to be xt plus 1. So the next step. So we are going to use a neural network based on the training from a ordinary differential equation solver. So the ordinary differential equation solver is going to produce these as a function of the number of initial conditions. So if you have 100 initial conditions, you're going to produce 100 trajectories. And then you can have the fine time stepping from t to t plus 1, which then defines the quality of your ODE solver. And you're going now to let the network make these predictions with a given input. You're going to predict the next stage, etc., etc. So this is, after we've defined these types of equations, which we're going to look at, this is a typical problem which we would solve with a feed-forward neural network. So an FFNN. Then we are going to move to recurrent neural networks, because this is again something which is very, very typical for recurrent neural networks. And then we're going to look at autoencoders. And finally, if of interest, we can also look at the general adversarial neural networks to predict the best possible results based on the training data which we have. So that's the basic framework for the first stage. So this will be path 1. Now, this path here, that can actually be extended. So let me just wipe out something which I have here. So this can be extended, can extend. So I was thinking that this could be the first stage where we explore these different methods, but with a simpler set of differential equations. And then this can be extended to partial differential equations. I know that some of you are interested in quantum mechanical problems. So this would be ideal for solving quantum mechanical problems. Can extend to partial differential equation. DE stands for differential equations, or just PDEs. So examples here would be Navier-Stokes equations, if some of you are dealing with fluid mechanics. It could also be the Schrödinger equation, if you're interested in that. And other types of differential equations. So that's one possible path, which then could actually define, so this would be the next step, which you could think of as a project 2 or part 2. So you could hand in just one big project and then present this for the final oral examination. Alternatively, you can split it in 2 parts, where you divert from this first stage and then look at, let's say, if you want to look at, let's say, just the solution of the Schrödinger's equation with autoencoders, that's fully possible, or other things which you would like to suggest. So keep in mind that we want you guys to have this kind of flexibility. The second path, which I would like to propose, is a more computational part, where you actually write own code for CNN based on your feed-forward neural network code and ANNs, or recurrent neural networks, and apply these to selected data, to data of your choice. And that could be the kind of data which I'm proposing in part 1, of your choice. So this means that you should now feel the freedom to actually develop your own codes for that. Path 3. So we are not going to, enforce that you should write your own code. You can use TensorFlow or PyTorch. So in part one here, you could use your own neural network code, which you have from PhysSDK, or if you prefer to use TensorFlow and PyTorch, which allows you to explore many more possibilities. So you would use TensorFlow to explore path one. So we could solve these differential equations, make the predictions using TensorFlow or PyTorch, or apply these, right, to own data. And I know that there are people among you who want to use, so as an example, if you're dealing with imaging, use CNNs to imaging. In the examples which you find on the GitHub address on previous projects, you will see that there were many students from high energy particle physics. And in that case, it's pretty common to actually have images from your reactions, the outputs of a reaction. And these are typical images from the detector, which are translated into pixels. And then you have to use these images to classify what kind of event came out of that specific reaction. So it could be a beta decay, you send out an electron, or you can have a gamma decay where you send out a photon, or you have more complex multi-particle events. So these are possible paths, and you should feel free to actually modify what I'm suggesting. But since we are going to cover some of these methods, actually we're going to discuss these 5 methods for deep learning. In the lectures, I'm going to use this path 1 in order to demonstrate the applications of these methods. So feel free to ask questions. I'm going to send you an email with these different paths and with the links to the codes and everything. But let me show you where you can find these codes. So, but before I do that, I wanted then to suggest a type of data set if we are now thinking of path 1. So if we go back to that. So one case which we have, case 1, is a simple one-dimensional differential equation where I have Newton's law, mdx dt, this is the acceleration, and that is given by a constant, so there's a spring force with a constant x, k, which is the spring constant. There is a term which deals with friction, so there is a parameter d of dx dt, and then in addition, so this is the velocity dependent friction term, and then there is an applied external force plus an F external, which will depend on position and time. It can depend on position and time, but we are going to let it depend on time. So that's the first code which you can use to generate data. So what you would do now is to set up, for this specific path, set up typically 100 initial conditions, and you can choose these randomly in order to solve the differential equation. So you could set up x0 and v0. So we are staying with a one-dimensional problem here. So you could set these up. And then what you would do then, when you set up these differential equations, then you would call the differential equation solver, which you find in the GitHub address. So call the ODE solver and generate. And in this case, we can just focus on the position. So we would generate x of t, which now comes as an array, where we have defined a delta t, a time step. Delta t, we could say that this is 10 to the minus 2 here. And then t would simply be an array where we now have a just a very simple way of using NumPy, a range. You've probably seen this function many times. And then we would have a 0 up to the t final. And this goes in steps of this delta t here. So that's one way to set up the integration points. And when you have the integration points, you would call the differential equation solvers, and you produce an array with xt's. And then you're going to do this for a series of initial conditions. So you could have something like 100 trajectories, depending on the parameters of the force, of the friction term, etc., etc. And then what you would set up then, when you have this range, so suppose now you have 100 initial conditions, then you would have a loop here for I in range. So suppose now that we did this, so we have 100 initial conditions. Then you would set up the input to the neural network as this x of t. And that would now depend on the previous time step. So you would start with time 0, initial conditions, and then you make a prediction for the first time step. And then you use the next time step to make a prediction for the output. So this will be the input to the neural network. And then you would have an output, which would be t plus 1. And then depending on how you have structured the data, whether this is a one-dimensional x or three-dimensional, etc., etc., you would need to set up the correct arrays. And I'm going to place online an example of a program where you can actually set up these inputs to a neural network. And then based on this, you can then look at the architecture of your neural network, and you can then, with the inputs and the outputs, you can then start making predictions and see if the network is able to predict these trajectories, which you have calculated with an ordinary differential solver. So the ordinary differential solver functions now as your data generator. And after we've generated the data, we are going to forget about the differential equation solver. So let me show you where you can find these codes. So this is the first simpler case. And if you look back at what we discussed here, we have a path 1, which is this one. The other path, which is a more complicated one, but the basic philosophy is essentially the same. So we would now define a set of differential equations where we have, these are coupled differential equations, and this is called the Lorentz attractor. And this is a little bit more complicated than the one we had before. So it's sigma is a constant. We have a dy dt, and this is x times rho minus c here, minus y. This is a so-called Lorentz attractor, and it's widely studied in chaos theory. And then we have a dc dt, and this is xy minus a parameter beta times z here. So again, you could choose a time step, delta t of 0.01. Here in the simulations, you could choose a final time in order to get enough information to 8. And then these parameters, which I would suggest, are parameters I took from a scientific article here. You could have beta 8/3, sigma equal to 10, and rho equal to 28. So these are parameters. And then you could then again define 100 random initial values for x0, y0, and c0. So I'm going to place a program which shows you how you can generate these. And then you would then produce, by calling the differential equation solver, you would have an x of t, and now x is a vector. So x contains x, y, and z. And this is going to be x of t plus your ordinary differential equation solver. And that can be an RK method, a Runge-Kutta method, a fourth order. And based on that, you would simply repeat this final stage, which you have here. When you have the xt values as arrays, as a function of time, and as a function of x, y, and z. So it's going to be an array, which now actually is a matrix with a given number of time steps and the values of x, y, and z. So what you would do then is to then generate, based on these x of t's, then you would generate a new neural network input, which is given by x of t, and a neural network output, which is just x of t plus 1. Alternatively, if you don't like what I propose, I won't be offended if you use other data sets. So that would be the path, the alternative 3. This would be own data sets. Now, the nice thing with this case here is that we can reuse these dynamical equations with recurrent neural networks, and we can reuse them also for autoencoders and generalized adversarial neural networks. So this gives us a lot of flexibility. And think also of using, if you don't want to use your own code, that you could use either PyTorch or TensorFlow. So this is path 1. If we go back and look at path 2, if you want to focus more on writing your own code, that's something which you can do and apply to data of your choice. And that could be the same data sets which we have here. These equations which we are looking at, or if you're more into, how to say, imaging for using CNNs, etc., path 3 could perhaps be more interesting. So just think of alternatives to what I'm proposing. That's a little bit about the philosophy of this course. So I will go along a path which deals more with solutions of differential equations, which is more my cup of tea also in my own research. And it's also the kind of topics I'm more interested in. Okay, so any questions so far? Okay, so as I said, I'm going to place online a code which does these final steps. What you will find if you now go online to the GitHub address is now a code here. So let me just bring up the if you look at this specific code, which is called ODE example, this is the one which solves Newton's equation. And we can take a closer look at this ODE example, which you have here. And let me just go through it. So this is the ordinary differential equation solver. So here I have a force, which is now simply given by a velocity-dependent term. V is the velocity. Gamma is the friction constant or air resistance. So we assume that there is a linear dependence on a damping term on velocity. There is an external applied force, which has a constant here times a cosine. So this is just a force, and then we have a constant x here. So these equations are all scaled. Now, there is a simple Runge-Kutta solver, which to fourth order, it's written in a very brute force way. So it's not very elegant. So this actually is specialized to this specific problem. If you want to look at the Lorentz attractor, you would have to make changes here so that you can look at the different derivatives. So in our case, we are mainly interested in for that specific case, which is a first order differential equation. Then you don't need to do as we have done here. So the Newton's equation is a second order differential equation, which we translate into two coupled first order differential equations, one for the velocity and one for the position. And I guess you're familiar with that. So in this specific case, when I call my differential equation solver, what this returns is now an array for velocities and positions as a function of time. And you can see now that I have an initial value for t, initial value for v, and x. Everything is set to 0. And then I have my constants, which define the force, the oscillation frequency, which is linked with the force. So I have a force which comes like a cosine t times the frequency multiplied with a constant. And here I then generate this data. So if you just look at this code here, if we just run it. No, wait, I had my, sorry, I have to look at my Jupyter notebook here. So if we just run this code, you will get something like this. So this is something which is ready-made for you to simply take out these arrays, which you get back, v, x, and so on. So you can take x of 0 and let that define one input. And then you produce x1 as a prediction, that's your output. And then you continue with x of t and x of t plus 1, and you produce the output for all the data sets which you have produced here. And then furthermore, you should run this for randomized initial conditions, or you could make an array of specific initial conditions. Any questions so far? Does this sound okay? So this is a simple equation, which many of you have encountered before, but which is a second-order differential equation. If we go back to this Lorentz attractor, that is a set of coupled first-order differential equations. So that means that we need a term for x, y, and z. And here I have the derivative of x, which is the velocity. And then I have the derivative of the velocity, which is the acceleration divided by mass. So in this case, mass is scaled to 1, which means that the force which you return here is actually the same as the acceleration, which is then the derivative of this quantity. So the only thing you will need to do then is to change this or make it more generic. So you can take in any kinds of derivatives. So in your case, you will need to define a function which calculates the derivatives. So this is if you want to do the Lorentz attractor. Alternatively, you can use this code which is here for a standard Newtonian problem. And as you can see, we are later going to use a recurrent neural network to make predictions about the path here. And later, we are going to move into autoencoders and GANs to solve the same type of equations. Then, if you go into the same folder, what you will find in that specific folder here, if we just move on, and you will find this code example for a neural network. Alternatively, you can go to the slides for this week, and the slides for this week contain then the links to the code from FIS SDK 4155. So if you go into this one, what you're going to find then is a code for actually setting up a neural network. So if you scroll down here, you will find some links to videos and neural networks. And then there's a quick review of the backpropagation algorithm. And what follows then is also a discussion of the ways you can build a simple feed-forward neural network code. So you can, many of you have seen this before. For those of you who are not too familiar, feel free to take a look at it. Alternatively, there is a nice program which was developed by Greg, who could not be with us now, but let's bring up that one. So this is an NN and the Jupyter notebook for that code. So in this specific function, what you will find now is an implementation of AutoGrad, which I would recommend to replace with JAX. And this contains ways to update the learning rate for the gradient descent. So in here, you will find different ways of doing the gradient descent. So one is the momentum gradient descent. And then we have these adaptive ways of changing the learning rate. So we have AdaGrad. We have AdaGrad with momentum as well. We have the root mean square propagation. And finally, we have ADAM. So these are ways to change the learning rates. And here, Greg and Eric have actually written a class which is called Scheduler. And then there's a class constant here where you don't change your learning rate. And then you have these different classes here where you now can update the learning rate. You can add momentum to the gradient descent method, and that normally speeds up the search for the roots of the gradients, and so on. And finally, what you also have are examples on how you would use these schedulers, and many of you are familiar with that. There's a set of cost functions, and you should feel free to define different types of cost functions. This has just a limited set of cost functions, like the standard mean squared error, and also the cross entropy. And then there's a log reg cost function, which is sometimes used. And feel free to use this function if you now want to write your own code. So we won't penalize you if you don't write your own code. If your attention is more on solving physics problems, what I would typically recommend then is to use either TensorFlow or PyTorch, depending on which one you're most familiar with. You can find examples on how to use the cost functions here. Then we have different activation functions, which many of you may have encountered, and their derivatives. And we discussed these in connection with a review of setting up a neural network. And here are examples on how to use the activation functions. You have access to all these codes, and then comes the code for the neural network with the feed-forward pass and the back-propagation pass. And since many of you have already taken PhysSDK, I would perhaps recommend that you either use your own code or that you just switch to TensorFlow. So when it comes to TensorFlow, there are examples. If we now go back to the lecture slides from PhysSDK, if you scroll down here after the simple implementation of a neural network, what you will have then, if you go down, 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 there is a TensorFlow example. So let's bring that up. So you would need to install TensorFlow, and we normally recommend to use Keras as an API on top of TensorFlow, unless you want to write codes in TensorFlow, which is actually a kind of library which allows you to redefine many of the standard Python functionalities through NumPy, etc. And then also to implement neural network deep or other deep learning methods. But the typical way you would use it is with Keras, which allows you to experiment very easily. So this is the example of a classification problem where we are going to look at handwritten numbers. And the way you would use TensorFlow then is to have a definition of what kind of model you want to use, whether this is a sequential one where you have the standard feed-forward pass, whether this is a dense network. You can specify different optimizers for the gradient descent. You have different regularization methods with their hyperparameters. And then you also have ways to use this one-hot encoding where you change the different labels here into bit strings. So in this case, you have 10 handwritten numbers. And that means that you would have a word of length 10 bits, which then encodes the different numbers here. So these pictures are pretty blurred because they have been scaled down from 28 times 28 pixels to 8 times 8. And there's a reduced selection of images so that you can actually do calculations within the time of a given lecture. So if I were to run this with a full case, I would not be able to terminate the demonstration within a regular lecture. So you would then introduce these. You would split into train and test as usual. You can also have a validation set if you prefer that, and include cross-validation, as many of you are familiar with. And then if you run that one, you're just setting up. Now, you know that when you're setting up the number of or you're performing a calculation with a stochastic gradient descent, we would typically split this in batch sizes, and hopefully then to be able to not be trapped in a local minimum. And we would have number of epochs so that we would typically just rerun the calculations. Here I have two layers, one with 100 nodes and another with 50. And the category is in the output layer, so we have only 10 output nodes because we have 10 given numbers. Now, if you're dealing with a regression problem like this solution of differential equations we've been looking at, what you would do then is simply not to have any activation functions in the output layer. You would just spit out the output. And then the setup of the network follows here. It's a sequential. I feed in the number of neurons, the categories, the parameters eta and lambda. Eta is the learning rate. I can define the type of activation functions. I define another activation function for the softmax, which is the final output layer. You can define a type of optimizer. So this is a stochastic gradient descent, which receives a parameter eta. And in that case, it doesn't do any calls to learning rate schedulers like ADA, GRAD, root mean square propagation, or ADAM. And he follows the metric. So you can now just run this, and then finally we will just run the whole network here. And this takes some time. We have two hidden layers. So this is going to take a little bit of time here. So it's normally going to take something like 5 minutes. And this is one possibility for the paths of the project here. So within the end of the week, I'm going to wrap up the final setup for the projects, or the first part here. And then we are going to continue the discussions of these topics next week. So next week, I wanted to discuss more in detail convolutional neural networks. So that means that we will be less focused on this specific case. But when we come to recurrent neural networks, then we are going to apply these to these differential equations. But I wanted to go through the mathematics and the basics of a convolutional neural network and show you how you can write your own code for that. But then most people end up using TensorFlow or PyTorch for convolutional neural networks, which is perhaps the most efficient way. But it's often useful to have it done yourself. Okay, so I'm going to stop this one here and go quickly back to the paths which we have. And I would like you to think a little bit about the possible paths which we can have for project number 1, or the first part. So the path which I will follow up in the lectures deals with solving differential equations. And then later we can move on to more complicated differential equations. Path 2 is more if you want to write your own code for, let's say, a CNN and a recurrent neural network. This is also something which can be of interest. And apply these to data of your choice, or you could use the data which I propose here. When it comes to these different methods, you should feel free also to elaborate on you writing an RNN if you want to do that. Alternatively, just use TensorFlow or PyTorch. And finally, path 3 is more you having specific data which are linked up with your, let's say, your master thesis or your PhD, and then you want to explore some of these methods on the data which you have in your thesis. And if you look into the folder, so let me just bring that one up again before we stop today. If you look into the GitHub address for the course, you will find a folder here which is called previous projects or earlier projects, and you will find examples on how convolutional neural networks have been applied to identifications of events in particle physics from particle physics experiments. Similarly, there's also an application of convolutional neural networks to the Higgs search and the classification of the Higgs. And in that case, people have also used gradient boosting. So there's a lot of flexibility here, and you should feel free to come up with your own paths. Alternatively, if you just want to follow these lectures and discuss and use these topics which I suggest, then feel free to work on these topics. So I hope there's not too much choice, or perhaps there's too much choice, but I want to leave this kind of flexibility to you guys. Okay, I'm going to stop the recording now.